Hey, everybody. Get started. So I'm thrilled today to be able to welcome back Violet, CLSP alum. So since leaving Hopkins, she's gone on to do a lot of really cool stuff in a lot of different areas, much of which should be no surprise is very relevant to us here at CLSP. I think basically she could have given a talk on probably about 4 different threads of work, and all of them would have been very exciting. Violet's been recognized as a thought leader in her area. While on Monday, we hosted a speaker who, as I said, is a rising president of EMNLP. Violet just won 3 outstanding papers at EMNLP. So we had to decide which of these do we think is most exciting. Congratulations. So yeah, so I'm really looking forward to this talk, and please take it away.
Yeah, thank you for the nice introduction, and it's very great to be able to come back and visit home. It's really like coming home. So it's my great pleasure and excitement to share some of my recent work on controllable and creative natural language generation. So I think creative generation haven't been a super popular topic, so I also want to give it a little bit of an introduction of what's creative AI. One thing is it's hard to really define what's creativity. Wikipedia gave this definition of creativity as the ability to form novel and valuable ideas. But here I want to give some of the case-based example, because I define it as a set of tasks that if AI have creativity, they should be able to solve. And here is an example from movie. It doesn't play. Let's see. Okay.
Oh, but who wants the screenshot?
Oh, okay.
Yeah. And then let's go back to the no, maybe you're scrolling. So I'm sure if you scroll down, you should find yes, that
Okay.
oh.
Okay.
I'm lying on the moon, my dear, I'll be there soon.
Okay, I'll stop here. How many people knows this movie and know what's the scene here? Okay, what's the movie? Her. And what's the scene here? It's a robot Samantha singing her song of the moon. So it's a song that the robot AI composed, and they sing it together, and it's how they build very deep connection with human. Okay, so this is creative AI in movies. We also see a lot of creative AI in news. For example, I think this is some old news. ChatGPT wrote my AP English essay and I passed. Okay. And this year, things get a little bit scary. ChatGPT is a terrifying subtext of writers, of the writers' strike that reshape Hollywood. Earlier this year, there's also this news: AI outperforms human in standardized tests of creative potential. So we see this creative AI happening. However, what's the reality? Actually, in preparation for this talk, on this Tuesday, I go talk to ChatGPT about poem generation. I said, can you write a homophonic poem for a homophone here and here? Here, I didn't give too much definition because ChatGPT, large language model, knows everything, right? Let's see how it does. It says, sure, here is a homophonic poem. I tried to style my pet here, but it turns out he didn't like the hair gel. Right? It's not a pun because, as we know, so I go on to say this is not a pun. You should use either here or here for only once in your pun. For example, the magician was so mad he pulled his hair out. Is a good pun. Can you try again? Okay, so here I give definition. I give one-shot example. Let's see how the model does. Got it. Here is another proper pun. I was going to comb my hair, but I just couldn't brush off the hair brand idea. Okay. Again, not a pun and not funny at all. In comparison, maybe it's funny in a different way, okay? but it's not funny as a pun. But here is our earlier work in 2019, that's before large language model. We say generate a pun, but here and here, the greyhound stopped to get a haircut. Okay, we only generated the language part, but I think it will be nicer if now AI can also go multi-model and generate the comment to associate with it, okay? There's another thing I also try with large language model. It's also a task we do is hyperbole, which is an intentional exaggeration. So what I do is I give it a few short example to show what's hyperbole, and I ask it to generate. So what I give is the blank part, which is a prompt. The mountain we visited is so big, what? The model generated, it has its own ecosystem, it has its own zip code at the summit, it has its own weather pattern, okay? Looks pretty good, right? Compelling because it's hyperbole and it seems to be appropriate. However, if I goes on to say, I went to a nearby garden that is so big, the flower, it says, has its own zip code, has its own ecosystem, has its own GPS navigation. In other words, no matter what type of prefix I give, as long as I say this is so big, such that it will say it has its own zip code, it has its own ecosystem. So it's very cliched expression. Apparently, this model have learned or memorized something that give you the impression that they are impressive, but they not necessarily have learned how to generate really creative expression. In comparison, again, this is some of our earlier work. Before large language model, we trained actually a 700, depending on how do you define large language model, we trained a 700 million, fine-tune a 700 million parameter model, and we were able to generate much more diverse and authentic expression of hyperboles for different things. We give the same, the mountain is so big, the garden is so big, and the forehead is so big. It's different expression. Okay, go ahead.
So these are clearly more diverse.
Yes.
Are the completion, do humans agree that the completions go better with the black text that they're associated with as opposed to the other black text?
Right, that's a good question. This work is done in 2021, whereas this is coming. So like, we didn't do comparison back then when we do this experiments, because this is ChatGPT that came after we do this job, we do this work. But I think the point I'm trying to make is a lot of times the large language model can give us the impression that they're doing very well, but if you repeatedly query them to do for different things, they will be not diverse. The diversity is an issue, whereas it wasn't an issue even for some of our earlier work with a weaker model. So in other words, we actually need to be more intentional in terms of how do you get this more uncommon expression. Okay, so I hope with all this example, I've already showcases what do I mean by creative AI. So then I want to also motivate why do we need creative AI? First, I think I want to cite Shannon, who set 4 goals for AI to achieve by 2001. So that's 20 years ago, okay? A chess playing program that can crown world champion, mathematical program that can prove Riemann hypothesis, the stock picking program that outperformed prime rate, and a poetry program that had a piece that can be accepted by New Yorker. I go ahead to generalize this poetry program into any creative composition program. And as you can see, among these 4 grand AI goals, the first and third is already achieved, whereas the second and fourth are still not achieved yet. So, and also even recent years, I think another thing is many people start to ask me, it seems large language model, ChatGPT are good at creative tasks. But I think when I give these examples, and also there are a study, this is not my study, it's a study this year, shows that large language model may give the false promises of their creativity by give layman the impression that they're good, whereas if we have experts to look into these pieces, they can clearly identify all sorts of issues of creative writing. Okay, so this is on the scientific part. Basically, I believe creative AI is a type of capability that we know if AI can do, then it's a big progress, and it's a good test bed for the progress of AI. On the other hand, there are also many applications of creative AI. For example, it can enhance engagement. I have some example of the advertisement for Coca-Cola. So these are some of their old advertisement. It says it's a real thing, and it talk about the taste. Whereas there are the right-hand side, it's some of the newer advertisement. It says, savor the magic of Coca-Cola. Okay. Do you think that the right-hand side is more creative and make you more likely to just try? This is on the engaging side. Another important thing we think creative AI can do is to lower barriers for layman. This will be one of the tasks I talk about today. So where we look into a task where we assume AI can help some people, in our case of 5-year children, the child, to write a song for their daddy's birthday, okay? And as you can see that the kid apparently have the motivation to do so, but they may not have enough expertise to really write a song. Another thing is people start to think when the AI getting creative, can they even help us generate novel ideas? I'm not sure how many people know this paper this year from Stanford, not my work, and I also don't want to comment on that, but basically they have a conclusion saying the large language model generated idea on prompt tuning actually are better than average or junior graduate student. I'm not agree with that, but what I'm saying is in the future, if AI are truly creative, then maybe they can start to help us form hypotheses and solve problems. And then finally, another application scenario is problem solving in unseen scenario. For example, whales was actually initially invented for pottery. However, later on, people combined it with access to become transportation. That really boosted our productivity. So we assume a creative AI can help us with all sorts of these tasks. So if you pay enough attention, you'll find my talk title is Controllable and Creative Generation. And as of now, all I talk about is creativity. There's nothing about control. How to connect them? Where is the connection? One thing I want to make as my take is I think creativity and constraints comes hand in hand. In general, to fulfill a meaningful goal in a constraint setting, one naturally has to be innovative. I have an example of some of this ancient story of how do you weigh an elephant, okay? It will be an easy problem if you just have a large scale, but then how do you weigh an elephant without a large scale? And also you cannot cut it into pieces. How do you do it? There was an ancient story where they put the elephant on the boat and see how much the boat sank into the water, and they put the same amount of rocks into the boat, sink to the same level, and they take it out to weigh. Okay, so this is an example to show you why creativity come with constraints hand in hand. So only when you try to achieve a goal under constraint, you will be creative. And this is another citation I get from this Tiago Fort, who is a content creator and author. He said, if you want to destroy someone's creativity, remove all their constraints. Okay, so with this, I want to say from now, I think what large language model can do well is one ingredient of creative generation, which is convergent thinking, which is come up with arbitrary uncommon idea. However, what is not good as is convergent thinking, which is finally put everything together to fulfill the intention. So this is where we need a goal or tools to compile the constraints and solve the problem. Okay, with this in mind, I want to take a closer look at why large language model then fall short in creativity. I have two major points. One is the auto-regressive nature of a large language model make it hard to impose any constraints into the generation process. Out of the box. Of course, we can do more things on top of it, but out of the box, it's hard to be creative because of the constraints. Another is my personal hot take, which is for now, the way we do generation from large language model is to sample mostly the high probability region. But if we do this, it's just mimicking existing surface form or pattern. So it's deviate from generate truly novel or creative content. So in other words, we want to have some ways so that we can explore the lower probability region. Okay, so with this, I'm going to talk about 3 works that my group have been doing around this direction. The first will be a novel application of controllable generation, which is melody to lyric generation. And then I will talk about 2 methodological paper on 2 paradigms of controllable generation. The first is insertion-based language model. Another is controllable tractable control of auto-regressive model with traceable density machine. Okay, let's first look at some fun applications. By the way, interrupt whenever you need, if you have any questions. Okay. So the first is the application paper where we look at melody to lyric generation in an unsupervised fashion, which means we assume we don't have aligned data from melody to lyrics. This was a collaboration with Alexa, where we imagine Alexa can be a companion or assistant for even a 5-year-old. It can come to say, Alexa, I want to write a song for my daddy's birthday. It has 40th birthday, and he had orange beard. He liked play games. As you can see, these lyrics can become very personal and then thus very fun for people to celebrate their event. And then we assume a computer agent can say, great, anything else you want to include? And then the user can continue to say, okay, let them know that I love him to the moon and all that. And then we then imagine the model can generate the song like this that include all the user given information like 40th birthday, orange bears, games, love him to the moon. So this is the imaginary scenario. As always, whenever we have a problem in hand, we want to first test whether large language model would have already solved our problem. So this is my conversation with ChatGPT. I say, compose a song verse for my daddy's birthday, set the tune to Mary Had a Little Lamb. This is a song it generated. Happy birthday to you, dear dad. You're the best we've ever had. With kind, the heart so kind and the spirit so free, you mean the world to our family. Okay, not bad, right? Actually pretty good. However, how does this sound with Mary Had a Little Lamb? We did our best to align the lyric with the song, and we also do the voice synthesizing. But because it came out too bad, I'll go ahead and sing this song for you, okay? Happy birthday to you, dear, that you are the best we've ever had, with a heart so kind and a spirit so free. You mean the world to our family. You always lend a helping hand in every way you understand. I think if you have some music background, even if you don't, even if you just like songs like music, you probably have already identified tons of issues, right? Very apparently, first, it ends every sentence in very strange places. Happy birthday to you, dear. Here is where the music ends. Then you are, it's another music end. And the best with, that's another where the music end. It's always the music end at some weird place that the sentence didn't end. And that shouldn't happen. And another thing is, for example, here, if you hear what I said, the heart so kind and the spirit, then here the spirit is a short word, whereas it aligned with 3 sound, it's very hard to send this out, okay? So in other words, if we take a step back and formalize this task, our input will be a music notes as melody, where we want to generate our lyrics to align with. And usually we will also collect some other keywords or title from the user to encapsulate their communicative intent. And then our output will be a lyric that will align with the melody and also incorporate all the user provided keywords or title, okay? And this is an example of aligned music, Mary Had a Little Lamb, and this is how well it sounds good. As it turns out, this is actually a very challenging task, mostly because there are lack of paired data. A lot of data out there, they are copyrighted and we cannot use them to train our model. So I view this problem as standard like vision language model or low resource machine translation model. So this is a SOTA baseline where what they do, I think they made every effort. They will do autoencoder on the melody modality and the lyric modality separately so that they can train their model. And then they use very limited melody to lyric data to train this cross-modality alignment so that they can then stitch the model together to encode the melodies and then decode the lyrics. Okay, so the drawback of this is apparently with so limited data, the quality is very bad. We will show later the quantitative results. And also because this is two different modalities, it's very hard to learn the mapping between the modality. And it's also have no control over the content based on this framework. In contrast, we have a completely different framework where we frame this completely as a controllable or constrained generation framework, where we will only train model to generate text, to generate a melody, where we'll take the input of the user title and then other salient words, we'll generate a plan. So we'll train this input to plan model, sequence to sequence model, or any large language model, fine-tuned. And then we'll train another plan to output model that convert the plan keywords into the actual song lyrics that include the keywords. But then the question is, now we only have lyric. It still cannot go with a melody. How do we make sure it goes with a melody? We do this decoding time constraint. So in other words, we will compile the melody into constraints, and then we will use this constraint to guide our generation so that the generation will fulfill the constraint, thus go with the melody. Go ahead, Jason.
Yeah, so two quick questions, but you're probably going to talk about this already. So maybe
Oh, okay. Okay, so the design principle is that, sorry, should I let you ask your question?
No, don't let
I will ask.
Okay, go ahead.
I know immediately it's
Yeah, go ahead.
So can you go back to the previous one?
Yeah.
Yeah, thanks for taking the question. I would think that the most important thing would be the rhythm and not the melody.
We also have rhythm constraints.
But I'm curious how important it is to actually know what the pitches are. Like you do just as well if you only have the rhythm. And I would think that the most important thing about the words is to know the stress patterns. And I notice in the lower right-hand corner between is stressed on the wrong syllable.
Right, that's all good questions. We will have some constraints, and this is the first that work towards this direction. So there are apparently more constraints, and we are working on any more constraints. I will talk about two constraints, including rhythm constraints that we compiled. But that's good questions. Okay, so this design principle, to summarize, it's circumvent the lack of melody lyric paired data. Like I said, this is unsupervised. We don't assume any aligned data for us to train. We only train on pure lyric data, text data. And then at the inference time, we will compile the given melody into constraints to guide the decoding such that it will generate the lyrics that can go with the melody. And then what melody constraints we compile? We, as Jason correctly pointed out, there are pitch constraint and there are many constraints. As a first work, we only look at two things. One is a segmentation constraint, and that is very pronounced in the Mary Had a Little Lamb song, the Happy Birthday song, where we know the music phrase should align with the segmentation of lyric sentences, which means usually when music end, your lyric sentence should end as well, and vice versa. And you want them to be aligned. And a good example is the original Mary Had a Little Lamb song. Okay. And the second constraint is the rhythm constraint, which is the music rhythm should align with the lyric meter. What does it mean? It means the shorter notes usually need to align with the unstressed sound. And then the longer lyric usually align with the stressed sound, but it's not enforced. So this is the example of a music node. As you can see, we can compile them into this constraint to show that there are two segments. The first segments have 8 syllable, the second have 6 syllable, and their stress pattern is unstressed, stress, unstressed, stress. That denoted by 0, 1, 0, 1. Okay, then with this constraint, we can actually do a lot of interesting thing with our model. The first thing is we actually need to do a multitask training or fine tuning of our model so that it can do syllabus planning, which means we want a sentence with 5 syllables or 10 syllables. We need the model to be able to do that. We fine tune a model to do it. But then after that, we also need to constrain decoding so that the lyric can go with the melody. And what we do is, at this point, I don't think it's very sophisticated. What we do is we take a word, we look up its pronunciation in the CMU dictionary, and we can, amazing, for example, we can compile them into unstressed, stress, unstressed pattern based on the pronunciation alone. And then when we decode, we will take the original, so we'll have original district probability of the next word, but we'll discount it with the constraints. So we'll basically multiply this alpha. And as you can see, when we enforce a hard constraint, which means they have to align, then alpha will be 0, which means if this violated constraint, this word will have 0 probability. We won't be able to sample it. However, we also have a version of soft constraint where alpha will be in between 0 and 1, which means we will give a discount. We'll discount the probability of the next token if it violates the constraint. Okay. So with this, I want to first go with a qualitative example. The same sound of Mary Had a Little Lamb generated by our system. Again, I will send this sound for you. Okay. Happy birthday to you, Dad. You and I celebrate all the memories of that day. We will cherish them. Now cake and candle for the joy. Love is here for a hug. Everywhere is filled with love. Together we are one. So as you can see, apparently it's not perfect, but the alignment is much, much better. Okay, and then it looks very natural sound. We also have done a lot of automatic and human evaluation, but in most of this creative generation, we rely on human evaluation much more. So this is human evaluation we do on 20 melodies and 100 sound, because on each melody, when we give different keywords, different title, we can generate different sounds. And then we will take some of the baseline model. For example, SongMass is a SOTA songwriting system. And then GPT-2 is a large language model. Lyra is our model with soft and hard constraint. And then the human lyrics. As you can see, we evaluate singability, interlegibility, which is a musicality, which means how much this lyric can sing with a given melody, and intelligibility is when people don't look at the lyric, how much they can understand what you're singing. And that's also a way to show how good the lyrics align with the melody. And another is the quality of the text, which is coherence, creativeness, and the right rhythm. As you can see, if we compare the two baselines, SongMass and GPT already surpassed the SOTA baseline by producing much more fluent texts. But then our method, Lyra, consistently outperform all the baselines. And then human is still much better, especially in terms of creativity, coherence, rhythm, and overall. So in other words, in our case, in order to enforce the constraint and let the lyrics go with the melody, we will sacrifice quite a lot on the quality of the generation. Okay. I think this is part for lyric generation. Any question? Go ahead.
I think this is really cool, and I can see how it's useful for lay people.
Mm-hmm.
But if you want to sell it to a professional songwriter, what other kinds of features?
That's a very good question. I have one slide towards the very end to talk about ongoing and future work. We do have a system where we have basically, it's an interactive system where we have 4 different steps where we hope it will help a professional songwriter. That's a submission to Kai. The short answer is very seasoned user. I think they still don't find it's very useful, but the starting song lyric writer, which are still professional, they find it useful, and also the quality judged by the more senior lyrics writer it was improved. Improved. Yeah. So there are several things that I will maybe show a little bit more that we think the model can help. Thank you. Any more questions? Okay, cool. Just one last thing is this same framework we actually initially proposed for sonnet generation, the poetry generation, because as you can see, sonnets also have a lot of this rhythm, rhyme pattern, and structure, and then this controllable generation or constraint decoding can be used to enforce all those constraints and generate good poems. Okay, so with these applications I now want to dive into a more technical part to talk about two different paradigms we have been exploring and I'm excited about for controllable generation. The first one is an insertion-based generation model called InSNet. And the idea or original motivation we have is that we know auto-regressive large language model struggles to incorporate lexical constraints. For example, when we generate poems or lyrics, we may want to plan out to say the first line we want to have word recall, time, and consider. The second line we want to have dark, gaze, stars. And also we want to consider stars to be the end of the sentence because they will encapsulate our rhyme pattern, for example. And then we will want our model to be able to incorporate all these keywords into the final generation. Okay, this turned out to be a challenging task for off-the-shelf auto-regressive model, and it's actually intractable under the auto-regressive formulation. So from here, we were thinking about an alternative formulation, which is insertion-based generation, which is somewhat like the mask language model, but it's not quite. So we're envisioning a way to generate sentence where we can start from anywhere. So for example, we can start from driving and we insert work on the right hand of the sequence. We have driving work. And then we insert to in between driving and work, we have driving to work. And then we can insert was to the left of the sequence, was driving to work. And then from there, we can also continue to generate Kim was driving to work, all the way to Kim was driving their new car to work. Okay, so this is an envision of insertion-based model. The benefit of this model is it's a much more flexible generation paradigm, and it can naturally handle lexical constraint because say I want to have a keywords of driving and work, I just give this as a model and they say hip insert. Then at the end of the generation, I'll definitely have these two words in my final output. Okay. And another thing is there are some prior work in this paradigm. Their motivation is also interesting. They try to look into how can they unsupervisedly mining linguistic structure. In other words, whether by training this insertion-based model, we can uncover the linguistic structure of the sentences so that the model will learn to first generate more important words and then gradually expand our tree. Another thing is it's also very good for continuously refine any completed sentence. It also showed in this example, for example, we can generate Kim was driving to work, and then we can say Kim was driving their new car to work. Similarly, we can say Tim was driving to work, and then we can generate Tim was driving his new car to work. So in other words, you can basically by insert and refine the content in the middle of the sentence to add the details. And that's a feature that existing auto-regressive models very hard to do. And finally, it turns out it's not our motivation, but when we look at the literature, there are also engineering benefit of this work. If people here work on some of the non-auto-regressive machine translation, you will know this model, because it can insert in multiple positions in the sentence, it can do parallel decoding. So then the decoding time will reduce from ON, N is the sequence length, to O of log N. That's another benefit. However, there are also challenges or a different formulation of the insertion-based model. First is, this is a very different paradigm of auto-regressive model, because if you recall auto-regressive language model, we always we get the representation of the last token, okay? And then we predict the next word. But here we need two things. One is a slot representation, another is insertion prediction. And what is slot representation? Say we have a partial context robot obey inning. So as you can see, we will have many slots. We'll have one slot in between any two adjacent word or token, okay? And then we need both sides of the information to represent a slot. Another is insertion prediction, again, in contrast to auto-regressive model, which only predict what word to end towards the end. We need to predict where to insert, which we call position prediction. Another is what to insert, which we call token prediction. So this is a very different paradigm. Another very practical challenge for insertion-based model is what we call volatile insertion position information, which is to say, if you are at step T and you have a partial sequence B, D, F, and if the next step T+1, you inserted 3 token A and C and E in this correspondent relation position slots, then if your step T positional encoding use absolute position encoding, then B will be position 0, D will be position 1, F will be position 2. But after the insertion, every token will change their position. Okay, so in other words, the traditional way of absolute position encoding will no longer work. And there are some naive solution for this, which is to just re-encode the whole sequence after each iteration of insertion. And that's some of the existing work, what they're doing, including insertion transformer, Levin-Shang transformer, and another work that from U Maryland. If you look at their complexity, basically they will have ON complexity, where this ON is the number of re-encoding of the whole context. And in contrast, the auto-regressive model only need to encode the whole context once during training. And we are the first, INSNet is the first work that achieved the same complexity as auto-regressive model, as an insertion-based model. Okay, so how do we do it? Go ahead. That's a good point. We actually ended up using modified relative position encoding. The naive positional encoding still won't work, but you have a very good intuition. Change it to relative position encoding will help. Okay, so we propose this smart positional encoding to encode the prefix, encode the position of the prefix. And we have 2 major requirements for this positional encoding. The first is the previously inserted token won't change their position encoding when the new token are inserted, right? That's a condition met in the auto-regressive language model, and that's why they can be very efficient. Another is it's easy to fulfill the first requirement if we don't have the second requirement, which is we still need to recover the absolute order of the tokens. Otherwise, we lose information of the whole sequence, right? Does that make sense? So the way we do it is we have a modified relative position encoding schema. Just as a quick recap of what's relative position encoding. Say we have a sentence, I have a pen, and then if we want to encode the position of then we will have plus and minus numbers to identify if the left-hand side it will be minus and the right-hand side it will be plus. And then the number is a distance. For example, half is to the left, the first token to the left, so it's -1. And then the period is the second token to the right, so it's +2. Okay, so this is how we use to encode our thing, but there is still another caveat. So there are transformers with relative position encoding, but it won't work for our thing. I'll maybe talk about it, why it doesn't work. But here is what we do for we call it insertion-oriented relative positional encoding, where, as you can see, we will always start with the start token and end token, and they will be encoded as 0. And then here we can say -1 means the start token is to the left-hand side of the end token, 1 token away at this position. Okay, later it will change, but here this is at this position. Now, when we insert, we will view this problem this way. So we will have a ground truth sentence, I have a pen, and assume we're inserting them in this order where we first insert have in between start and end, and we will insert pen after have, which is in between have and end, right? And we'll insert I in between beginning and have. Okay, so that's how we do it. And we will end up with a positional encoding when we insert have. What will be our positional encoding? S will be, the beginning of the sentence will be to the left of have. And how many tokens away? As of now, 1 token away, right? We insert have in between beginning and end. So it will be -1. And how about the end of the sequence token? +1, exactly. Okay, so this is our thing. Now we have and then we insert pen to the right of have. Okay, what will be the beginning of the token? What will be the relative position? It's to the left of pen. How many tokens away? 2 tokens away, so it's -2. How about the end token? +1, exactly. How about have? Have is, look at the ground truth. Have is to the left of the pen, right? How many tokens away? As of now, 1 tokens away, right? So it's -2, 1, -1, 0. 0 means this current token pen is itself, okay? So then we can just keep growing our context. And this is what we end up with, okay? And a good thing is if we permute it back into a natural view, what does it mean by natural view? This first view is how the tokens are inserted, but we know what is the actual sequence, which is I have a pen. If we permute it back with their order, you can see that, for example, because punctuation is the last token that get inserted, it will have all the position information of all the existing token, and the order is also correct. So as you can see in this encoding, we did satisfy the 2 conditions we said. The first is the already inserted token won't change their positional encoding. And then at the end of the day, the whole sequence will still have the information of the whole sequence. Okay. Does that make sense? So there is a comparison between the absolute position, where here we use this cross out to show if we need to use absolute position, after each insertion, we will have to update the token positional information, and every step we need to update. So it's not sustainable. Whereas the vanilla relative positional encoding, it actually assumes we know how many tokens a priori of the whole sequence. For example, here, S, we know the beginning token is to the left, but 6 tokens away from the end, because we know the sentence have 6 tokens in total, which is a wrong assumption. It's a unrealistic assumption for an insertion-based model if you want to grow, because you don't know. Here, our decoding is very different. And also, all the inserted token won't be able to know the right-hand side context. That's why we'll have this lower triangular feature of our positional encoding. Okay, so this is to show what's the difference between our positional encoding in one view and in another view versus some of the popular or existing standard positional encoding of large language of transformer. Okay, so with this, we need to encode the model. Okay, we will need to do 2 things. One is context encoding, another is insertion prediction. The magic we're able to do is we are able to only encode the context once. That's where the O1 come from. But we can use the same encoded context to do the insertion prediction many times. And then the trick we do it, as Daniel have already pointed out, this is a relative positional encoding for transformers. So here I rely on your background knowledge of transformer with relative positional encoding on how do we. So I have some equation here. If you know the standard transformer with relative positional encoding, you'll find this is the standard formulation. The only thing is the position encoding here R is different. Our positional encoding is different from the traditional relative positional encoding. The matrix is different. Otherwise, all the other computation is the same. If you're not familiar with this, then the only high-level message, don't worry. The high-level message you should know is there is an existing method to encode transformer with relative position encoding. All we do is to change the relative positional encoding into our relative positional encoding, and all the rest is the same as them. So after that, we will be able to encode the whole sequence. It's using transformer with relative positional encoding. The last thing is still how do we train this model? Because like we said, it's different. It's not always next word prediction. Every time we need to predict where to insert and what to insert. And as you can see, once we encode the whole sequence, we can do multiple different steps. At the very beginning, we only have a start and end token. That's something we don't predict, we give it. And we will predict where to insert the first token B. In this case, how many slots we have when we start with the beginning and end sequence? One, exactly. We only have one slot. Okay, so there is not much we can do, but as you can see, we represent the slot with the left-hand side token, the right-hand side token, and the last token. In this case, the last token is the right-hand token. And we only have one slot. But once we insert B in between beginning and end, how many slots we have now? Two, exactly. We now have two slots. And as you can see, we again can represent each of the slots with the left-hand side token, the right-hand side token, and the last token. The last token is the last inserted token B, right? So this is our first slot, which is in between beginning and B. And our second slot is in between B and N token. Does that make sense? And then as it grows, we'll have more slots, and we can always represent our slots with the left-hand side token, right-hand side token, and last token. The reason we need the last token is because sometimes after the inserting, we will still have the same slot, have a slot that with the same left-hand side and right-hand side token because we didn't insert anything in that particular slot. But the context have already changed because the last slot have changed, okay? So this is how we represent. And this is also our final training objective to highlight the differences. We have three terms instead of only one term in auto-regressive model. So we have position likelihood to predict which position to insert. And we have token likelihood, that's more like an auto-regressive model, to predict what to insert. And we also have a termination likelihood, which is under this context, given this partial context, whether we stop insert or we continue to insert, okay? So this is how we train our model. And this is some of the qualitative example where our input can be they decided start focus on. That's the keywords we want to incorporate. Here, I just want to give you an example to show what's the model behavior. For easier presentation, I grouped 3 steps together, but I color code the color, which means the insertion is orange, green, and blue, which means the punctuation is first inserted, and then the is the second inserted, to is the third inserted. And next is insert another punctuation, and then inserted he and inserted get. Okay, so it can keep going, expanding the context. And another thing I want to show is at step 12, we actually end up with a full sentence, but on the next day, he decided to get started to focus on the core, okay? But the model didn't decide to stop because the termination loss is not high. So it continued to generate and end up to stop in step 17 with another complete sentence. Okay, you have a question? Just
Yeah, so I may have missed something about how you trained it.
This is how I train. Oh, how do I get my data? Is it?
What order do you ask it to generate?
Right, exactly. So for the training, what we do is we take the ground truth sentences in the wild and we'll randomly permute them.
Oh, okay, yeah. So
the permutation will be our insertion order. Right. Exactly. Yeah. Okay, that's a good question. Go ahead.
Inserting things.
Mm-hmm.
It is true that I guess this is all one.
Mm-hmm.
You're in practice, do you think this is costlier than next token prediction? I suppose in your implementation, you probably need to like slice your tensors and like maybe add an image in the middle of it, which clearly might be like more complex than just adding predicting.
Right. Yeah, I think you are right. There is one thing that's more than so the encoding of this whole context is the same as so basically when we get here, it's the same as transformer with relative position encoding. What we do need to do more is we need to do this aggregation to get slot representation. This is additional step that will need more time, but we worked out a efficient implementation as here as well. Right, this is more costly, but otherwise it's comparable. Go ahead.
So this is a follow-up to my earlier question.
Okay.
I've always wondered when people are generating out of order, why they try to make all the permutations probable.
Right.
Like if you did a BAE and you said there's a latent permutation variable, you could say, let's just try to find one ordering, which was good to generate. And that might generate, for example, the syntactic dependence of a head word after you generate the head word and not before. So, there are some orders that are easy to generate the sentence in, and other ones that are hard, and you only need to generate it one way.
Right. I think
so it would be worth. Would it be worth trying it?
Yeah, that's a good question. We actually have some effort, although it's a little slow. We're trying to explore the order. For example, we first parse the sentence, and then we can follow the parse tree to take the first layer, second layer, third layer of the parse tree as our order. That's some of the effort we're trying to do. And we also have some effort of try to scale up the pre-training of these models. A lot of things, but I think that's a valid point. But this is more like this is a first work, and we'll just want to get it out. Yeah. Okay, so we'll move to a little bit. I'm run out of time, I think. Move to the quantitative result. Here, we're just to show InSNet is the first bar, and we evaluate on Yelp review generation, which is you give several keywords, it will generate a restaurant review for you. Similarly, news generation, you give several keywords, it will generate a news for you. And we're comparing with several mostly insertion-based model. And then plan right is an auto-regressive model, but then with first plan out keywords and do a sequence to sequence model to generate. As you can see, the InSNet consistently outperform these models. This is the automatic evaluation of just blue 2 and blue 4. Outperform these models. Another thing is this pointer model, it was the existing SOTA model back then when we do it. It built on top of BERT, I believe, a pre-trained model, whereas our model is trained from scratch on the corresponding data, and we were still able to outperform this model. We also have tried another task of machine translation because, like I said, a lot of non-autoregressive language model have application in machine translation with the motivation of reduce the inference latency. And we were also very comparable with some of the famous insertion transformer or Levenshan transformer in terms of both the latency as well as the blue score. This is a WMT Romania to English translation. I think I'm not sure whether I have time to go over this last work, which I'm also very excited about. Another paradigm of controllable generation. We will discuss it in Europe's 2024. So if you're going there, I'm happy to talk to you about this. We have a previous work that was last year, ICML was selected as oral paper, where the idea is, I will be very brief. The idea is to use a tractable density function to guide the autoregressive model. So the high level thing is we all know that now that models, large language model with prompts can generate things. For example, we can say we want a logical constraint of generate a sentence containing keywords winter, and we have our prefix, the weather is, right? We can prompt the model to say, please generate a sentence that contain the word winter, and this is my prefix, and it will generate, right? Apparently for autoregressive model, what we only have is a prefix given the probability of the next token given the prefix. And then if we don't have any condition over our constraint, then the weather is, it can be warm, it can be cold, okay? And maybe warm have higher probability, but what we really want is the probability of the next token given the prefix and our condition, which means we want to guarantee this condition is satisfied. We want the winter to appear subsequently. Then we want a distribution that can factor in this constraint and we'll be able to say cold, then we'll have much higher probability than warm under this constraints. But build a language model to be able to estimate the next token probability given the prefix and the condition, which means the condition must be satisfied. It's an intractable problem. But then how do we do it? We can apply Bayes' rule to this next token given prefix and condition can be factored into the condition being satisfied given the prefix and next token, as well as the next token just give the prefix. As you can see, the highlighted yellow part is just a standard language model. And this part, the blue part, is still intractable under a large language model, because in order to know, given the prefix and next token, what's the probability my constraint to be satisfied, we need to marginalize all the future tokens. Okay, so that's intractable. But what we can do is we can train a hidden Markov model that will mimic, basically will have a similar distribution, will approximate the language model distribution as close as possible. And then we can approximate this blue part with HMM. Because the good thing is HMM is a type of model that we can do efficient marginal inference and then sum over all the future context. However, even with this efficient model, tractable model like HMM, not all the constraints can be compiled and then be efficiently inferenced. And what we figure out is if our alpha, the constraint, can be compiled into a DFA, deterministic finite automata, then that's the group of a family of constraints that we can solve in our model. I hope Jason still offer automata in the NLP class. Do people recognize what this automata is accepting? What's the constraint here?
Gets and then cold.
Exactly. It's a sentence that contains a sequence, a phrase of gets code. Okay, so this is just an example, and you can imagine, I think many people work on speech also very familiar with what you can compile. Okay, so with DFA, we can compile the constraints of a set of phrase or words must or must not appear in our sequence, or we want exact keywords or key sentences or key paragraphs, or only some words from a given vocabulary can be included. In other words, any regular expression can be compiled into a DFA, and then we can, after we compile this DFA, we can use that to guide us to do marginal inference on HMM to estimate this which is the constraint satisfaction given the prefix and next word under HMM model. And then this whole thing, thanks to my collaborator, they have a tensorized efficient implementation that can be executed on GPUs, the whole thing. So this is a high level summary of what we do is we will use a large language model to distill a HMM, which can then use to do the marginalized inference over certain constraints. And then we will use this constraint to guide the probability during the inference time so that we can guarantee the generation satisfy our constraint. And we've actually tried several different experiments, but what I want to highlight here, what we can do as an application is to have interactive text editing where the user can ask a large language model to either insert any paragraph or any segmentation or continue something with additional constraints. And what we do is we take a Tulu, which is an instruction-tuned llama model with HMM with 2 billion parameter. We really scale up the HMM with very high hidden layer. And then we build a front end where we really allow user to interactively work with it. And this is an example of what the generation would look like. They have this first, they've defeated a small quad blank. Are few humans left, and despite their magical power, their numbers are getting fewer. Okay, user can come in to say fill in the blank using key phrase aliens mothership far from over. Generated text must contain 25 to 30 words. Okay, this is type of constraints we're giving, and this is what our model can generate, where it generates a very coherent context. In filling in the context, include the word alien mothership and far from over, and also complying with the word count constraints. Okay, so this is what our model can do. We also have conducted a quantitative evaluation. And as you can see, we evaluate the quality of texts, the success rate, which means how much times it really satisfies all the constraints. And you can see, because our method is a method that can guarantee the success of constraints, whereas all these GPT-4, GPT-3 have very low some constraint satisfaction. And then finally, we have this overall, which is the overall quality given when it satisfies constraint. And as you can see, if we don't consider constraint, GPT-4 have higher quality, standalone quality of the text. However, when we consider overall, our model is much better with a 7 billion model is much better than GPT-4 and GPT-3.5. I have a demo of our system, but I don't think I will have time to demo this. If you're interested, we can talk more, or I can demo this to you offline, but this is our interface. Okay, so with this, is there any question about this part? No, I want to switch gear to talk about the ongoing and future research in my group. My group mostly work on three things. One is controllable and creative generation. The second is evaluation of large language model in terms of safety, hallucination, bias, fairness, cultural inclusivity, as well as multilingual, multimodal, event-centric natural language understanding and reasoning. For today, apparently, I only talked about the first part, which is a controllable and creative generation. But I want to quickly highlight some of our work on evaluating large language models in all sorts of interesting aspects. For example, for creative task, we ask how good machine-generated stories or narratives compare with human. And as you can see in our visualization, the human stories are much more diverse with different story arc, whereas the machine stories are not diverse and also converge mostly into this story arc called ranks to riches, which means it starts low and then it goes, this person go become better, and then it ends in a climax. Similarly, there are other things that if we compare and contrast, human and machine stories, we'll find there are still a lot of things missing in large language model generated narratives, especially on the discourse level aspects like story arc, turning point, and affective dimensions. Another thing we do is we're the first to ask this question. A lot of the evaluation on large language model is on the text quality, like how coherent they are, how relevant they are, how helpful they are. However, people haven't been asked the psychological depth of large language model, which is how much they can touch people, because they are more and more integrated in our life. How much the stories generated by large language models will be able to have established connection and persuade people. So we establish what we call psychological depth scale, where we evaluate emotion, provocation, empathy, engagement, authenticity, and narrative complexity. And we show that with this defining factor that is motivated by theory, reader receptive theory, humans can consistently agree with people on all these aspects of psychological depth with very high Quipendorf alpha. Another thing we find, which is interesting or maybe sad, is GPT-4 now, in terms of the psychological depth, matches amateur human when tasked with writing short stories. very short story. We also evaluate large language model on creative problem solving, such as, for example, if you want to hit the leftover pizza in the hotel room, but there is no microwave, you only have an iron, a pair of socks, a coffee mug, a notepad, and all that. Like, how do you solve this problem? This is also, I think, a very interesting, fun problem. What we show was that the machine is actually doing better than we expect it can do in creative problem solving. Still gap to human, but the gap was not large. We also evaluate large language model cultural awareness. Let's see, that's on the evaluation side. Another thing is the controllable generation. I only talk about the application of creative generation, but actually there are much more things we can do. For example, we can also use controllable generation for story visualization. This touches multimodality, where we can also generate visuals to go with texts. That's some work we do. Another thing we find is controllable generation can be helpful for an OU task, for information extraction task. Because as maybe most of you know, since T5, people just frame all sorts of tasks as sequence to sequence tasks. Similarly, we can do information extraction as we give input passage and we generate a templated output texts so that we can parse out the information. So the information extraction, we want really to have this table style structure content, but we can generate the template output so that we can easily parse out the information to fill in the table. So this is one of the work we've done and we show it actually perform very well for information extraction. But something we haven't, where it's ongoing, we haven't really show is that combine the regular language model with constrained decoding, we can improve the performance of this type of extraction tasks. Let's see. And we also show that with controllable generation, it may be able to help us solve other like mathematical reasoning problem in the sense that we want to disentangle problem solving, which we want to let language model do, from format adherence, because usually we will ask the model to solve the problem. This is a general instruction, as well as follow certain formats so that we can easily evaluate how good the model do. And there are existing work, and we also have some work verify that whenever you ask the model to simultaneously solve the problem and follow the format, the performance will drop when the model have to balance the format. And we want to combine our technique with prompt-based technique to improve the reasoning capability of the model. That's another thing, co-creation, human machine collaboration. I think to answer Kevin's question, we also have this recent study under submission to Kai on how can we use some of our tools to help even professional songwriters to write songs. And what we find was useful based on our user study is this ideation, which is what word to use, what rhyme word to use particularly, as well as this fitting, which is how to fit the lyrics into the music, are two mechanisms, two components that are helpful for even semi-professional writers. The final thing I want to mention, I promise the final thing, is to do a large-scale pre-training of the internet. That's what I mentioned, and we were able to train some like smaller size 200 million size the model on all the Wikipedia and book corpus data set. And this is what we can show here on some NOU tasks. I think what's exciting here is apparently we're much better than all the auto-regressive models trained on the same data. And we are even better than BERT, but slightly shy of Roberta performance, which is apparent. Okay, so to conclude the talk, I talk about creativity, AI creativity, and I think large language model simply mimicking existing materials are unlikely to generate truly novel and creative content. And my hot take is creative generation is constrained optimization. We need to fulfill meaningful goal with under a constraint setting. So in order to do that, one naturally has to be creative. So based on this, we explore some paradigms for controllable generation and creative generation, including insertion-based model, and then a control large language model with tractable probabilistic model. And I also showed many applications of controllable generation beyond creative generation to show that this is actually a very interesting and practical area. And thank you for your time with us. I'm happy to take any additional question.
Great, then we're out of time. We had lots of time.
Right. Okay, thank you.
Hey, great talking. Now we get to feed you. Are
Right.
we going to Gertrude's?
Actually, oh, you
No.
guys are good, but
Yeah.
I'm not going. I'm going to you.
Gertrude's? Do you know?
Organize something else.
Did I organize it? Was I supposed to organize it?
I had a question, but it's not.
What's the question?
It's about, don't worry, I asked. It's about the diversity and
Hang on.
stuff.
Oh,
I'm thinking about it a lot.
okay.
I was gonna organize it for Monday.
Okay.
Fantastic. This is the only talk, David Seymour job talks. He's the only one I've heard singing it. So that was really.
That's, yeah,
really
I think the student was a little nervous when I say I have audios.
Yeah.
Is it right? Do you have audio? And then another reason I
Oh,
didn't play the audios I
okay.
prepared for the sound. One thing
Okay,
is it's
I did
really-
suggest it. All right.
Yeah.
Oh, we have to
so
get
I
over there.
said sound.
The
Another
singing was
reason-
great.
Yeah.
Another reason I
Okay, but there's no
figured
reservation,
the
so hopefully
equipment
there'll
is
be
also
space.
expensive.
Who-
Yeah.
How many people are
They
going?
didn't expect I would play audios.
Don't worry about it.
Anyway.
No, the scene was really phenomenal.
Not you.
It was really lovely.
Oh, you're not well. Oh, I'm sorry to hear that.
Thank you.
It was really
Do
good.
you have COVID or?
We'll be in touch. Enjoy
Right.
the rest of your visit.
Thank you.
Sorry, I can't spend time with you.
No worries. You're not going to New York.
No.
Yeah, no, that's fine.
we keep missing each
I
other.
think you mentioned
I
a
thought
couple
I
of you, like,
would.
call the other day.
So it's just
Yeah.
This is my daughter.
Yesterday,
I
you were-
see. Yeah, I wanted to go, but I didn't.
She loved it.
You have to teach today?
She loved it. She went to
Nice.
all the booths. She went to
Wow.
posters.
Okay,
Yeah,
wow.
she was really
How
good
old
at it.
is she?
14.
Oh,
But
okay.
no one
Good
thought
time
she was
to get into.
14.
Oh,
Everyone
okay.
just assumed she was a grad student.
Oh, wow.
So she had a really good time. Anyway,
Okay.
all right. How do you guys enjoy lunch?
All right, yeah.
Really
We
excellent
we
talk.
have to
Wonderful to see you.
get her somewhere at 2:30.
I was supposed to go to lunch with you today,
Um,
but I'm
I can
not
look it up.
feeling good.
Oh,
Um,
okay.
So I will
Yeah,
meet you later today, possibly
Okay.
outside, just.
Okay,
I've been ill for 9 days now,
Okay,
so I'm
thank you
probably
for
not
coming.
contagious.
yeah.
But really enjoyed your talk, excellent work as
Yeah.
always.
Thank
yeah,
you.
we have to, I think we have to get her somewhere at
Yeah,
2:30
Yeah,
sharp.
look forward to
Um,
chatting with you
So
more
just,
after.
it's actually me at 2:30, so.
Oh, it's you at 2:30?
Yeah.
Okay, great.
So with your time, I probably will be with Violet outdoors,
Okay, that's fine.
Yeah.
Um,
but just let me know when you're back.
And then Ben's.
yeah, I have to teach at 3 and I need to prepare a little for teaching, so I also want to be done at 2:30.
There's an opening at 4:30. I don't know if that's still true.
To do the nice.
Okay, yeah, so you want to go upstairs? Okay,
Okay.
we'll meet you by the archway in just a few minutes.
Oh, okay.
Oh,
I'll
good.
just maybe walk out with you. or-
Yeah, we're just gonna go get our jackets.
Oh, okay,
Yeah,
sure.
okay, so we'll meet you by the archway on the first floor.
Okay,
Yeah.
yes.
The archway, it's the archway.
It goes through the building.
Oh,
The whole building is an arch,
I'll make sure she gets there.
Yeah.
just like the exit.
Okay, okay, yeah.
Well, I went to, where I did undergrad, they had a big art, like, hey, I'm gonna see you in a little bit, great talk. So I think of that as a big art of the university. I'm gonna say no, but if you showed me pictures and you said it's not something, or drawings, we're always. But if you're asking, but wait, is that a requirement? I guess, no, it's not a requirement. Is that an answer? I just wouldn't call it, I guess I wouldn't call it an archway. How do I hang this up? Where's the?